tutti. Passo in inglese per salutare meglio i nostri amici che vengono da fuori. Anche il talk sarà in inglese. Good morning everybody. If you want to come closer, seats are free. Don't be afraid. We have Danilo today, which is a Linux engineer. He loves to tinker with low-level system things in many places. He works now at SUSE, and he is contributing to many things about the Linux stack. And today he will talk us about the new interesting features added to the boot process of Linux, from cryptography to an interesting feature like soft reboot, the ability to reboot only the user space. Hope you enjoy. Please, Danilo.
Thank you. Hello, everybody. So today we are talking about the boot process, and I will be talking about a couple of new features that got added in the latest years. So before talking about the let's see. Yes, now it works. Big hug from the penguins for the MOCA camp. I'm Danilo Spinella, and I'm currently working at SUSE. And today we'll be talking, first of all, about the boot process, the legacy boot process and the modern one. We will be talking about the new specification, the bootloader specification, which is currently not implemented by all bootloaders, but is something that is getting a lot of tractions. And then we'll be talking about the DPM2. During these days at MOCA Camp, we talk a lot about trusted computing chips that we have on the system that we can trust. TPM is one of them, and it's actually many actors in the Linux world are pushing to use it more and more. So we'll be talking about one use case that we can have for the TPM during the boot process. And last of all, we'll be talking about the user space reboot. So let's start. Boot process. The legacy boot, we had the BIOS, which was actually implemented back in 43 years ago, I guess. So yes, that's pretty legacy. Then we had the master boot record, which was the partition table schema. And we had the bootloader. Then the bootloader loaded the kernel. And lastly, the kernel loaded the init. This was how the boot process back in the days worked for Linux. Let's talk a little bit more about details regarding the legacy boot. So at the start, we have the BIOS. The BIOS got into the active disk. It has the first segment of the disk, which was the MBR, and the master boot record contained the first stage of grab. This MBR was actually really small. I think it was 512 bytes, which is pretty small, and it just loaded another part of the boot, which we call stage 1.5. And the stage 1.5 was actually just 30 kilobytes, so it's still pretty small. We go one step further. We load stage 2, which in this case, we can say that grab was working at stage 2. And grab loads all the different files, drivers, kernel images, images for the boot menu and so on, and they are loaded from boot grab. Then we have the kernel loaded into memory, and we execute bin init. So this is how originally it worked with Linux and grab2. Many different steps. Then UEFI came along. UEFI is the open standard, and it was designed to overcome BIOS limitation. BIOS was designed 43 years ago, so by the late 90s, many industries, many actors like Intel were trying to overcome these limitations, so they get together, they write the specification, and they try to improve a lot the boot process. So one of the first things that they did was to create a new partition table schema, which is called Greedy Partition Table, GPT, and it is actually part of UEFI. Yes, it was written many, many years ago, but it got wide adoption during the 2014. And actually, right now, if you install any system, GPT is always the default choice, because why use MBR? Let's see just a little bit more details about the difference between MBR and GPT. So in this case, we are still using the BIOS, no changes from UEFI, just MBR versus GPT. We can see that the first part, this is the entire disk. The first part of the disk is the MBR sector, and it is true for both the MBR and GPT. The first part, the MBR partition hard disk, is going to boot, so the first stage of the BIOS, MBR is read, the MBR then stage 1 loads stage 1.5, the stage 1.5 loads stage 2, and so on. So we got to boot.grab, and then we start the system. The difference here is that with GPT, we don't need to use the first sector of the drive to contain the stage 1 or stage 1.5. We can directly have a different file put somewhere else. Like you can see here, core image is put in SDA2, which is far away from the start. And we can just use it to boot the system. Why do we still have the MBR sector for both MBR and GPT? This is because while GPT was getting traction from all the different utilities, like for example, think about partition tools for Linux. While it was getting tractions, people didn't want to mistakenly erase their drives. So what they did was had this MBR sector at the start of GPT, so that every tool that didn't support GPT was able to actually understand that this was a hard drive with a partition table and so on. So the drive was safe. Let's talk a little bit about how UEFI changed the way that the boot process works. So first of all, UEFI, as part of specification, say that the firmware itself, or the various devices, needed to implement a boot manager. So basically, we don't need anymore to have a stage 1, a stage 1.5, because UEFI will act as one. UEFI is able, or at least the standard that UEFI defines, that all computers right now implement, says that the firmware needs to work as a boot manager. This creates quite a lot of quirks, but at the same time, it helps a lot, because we don't need to think about the MBR partition, the stage 1. We can just focus on the bootloader, boot manager, focus on grab, system deboot, whatever we need. And so what actually means that it can work as a boot manager? It means that it can chain load another bootloader. So for example, if you start with UEFI and you see grab, it means that the firmware that your computer is implementing the UEFI standard, it means that it loaded grab. At the same time, we don't need to chain load another bootloader, but we can just directly load an image, for example. We can load the kernel directly. UEFI is able to directly boot inside the kernel. And also one other thing that got added was the secure boot. By having keys, SAGNet keys inside in this case, TPM, we are able to ensure that nobody tampered with the bootloader. This is because just a couple of distributions, and Microsoft as well, they signed their bootloaders. So the secure boot just checked that this bootloader was actually signed by a proper entity, like Microsoft, Fedora, Ubuntu. They are signing the bootloader as well. And this has just a little bit more security. Many times, if you want to install a distribution that, for example, is not is doesn't have a lot of mainstream support, then you need to disable secure boot. I think there is something that many of us needed to do while installing Linux. I see somebody nodding there, so they they get it. So let's just have a look at the EFI system partition. So this is the partition defined by the UEFI standard. And we can see this is actually the partition that I have on my laptop. We can see different files. So one thing that strikes us is that we have different folders, and every folder contains some EFI file. So the one that I want to put the attention into is the OpenSUSE one. Is the one that is currently booting my computer. And we can see that we have grab.efi and grabx64.efi. This is the partition, the grab bootloader that will be loaded by the UEFI firmware. We can see also here that I had previously Microsoft installed here. It came with Microsoft. I'm really sorry about that. But some files remained on the SP partition. I didn't format it. And this also reveals one big issue that we have with this setup. Basically, every time that we install a new bootloader, for example, we install OpenSUSE, Tumbleweed, then we install Ubuntu, then we install an encrypted Gen 2 system. What happens then? Every distribution, every system just install its own grab inside the SP partition. This also means that grab needs to recognize all other systems for every system that you install. So the OpenSUSE grab needs to recognize OpenSUSE, kernel, and images. It needs to recognize Ubuntu, and it needs to have access to Gen 2 files, Gen 2 file system to read the kernel and know that there is an encrypted system of Gen 2. And this quite becomes messy pretty soon. For example, maybe we need to, maybe the default grab that we are using is from OpenSUSE, but we wanted the one from Ubuntu. We need to go into the BIOS, change the order, and it's something quite messy. So what happened is that they came up with a new standard, and this actually is the main part of the presentation. This is the new standard that is a specification. You can find it online. It's pretty big because it tries to covers all use cases, both desktop, servers, security. It is pretty big. So, but in this case, we'll just see a small bits just to understand why this thing got implemented here, what are the advantages, and what can we use it, what we will see in a couple of months. So, first of all, it's just a set of file formats and naming conventions. And the important part for us in this case is just that it allows sharing menu entries between bootloaders. So, for example, I've installed OpenSUSE Tumbleweed. Then OpenSUSE Tumbleweed will have its own menu entry specified by the bootloader specification. And then Ubuntu will come, will read, grab from Ubuntu, will come and read the menu entry from OpenSUSE Tumbleweed, and we'll be able to load both of them. Let's have a better example. So the bootloader specification defines two different entries. The first one is a text-based one. You can see here that is contained inside bootloader entries. The bootloader specification, contrary to what we used before, the ESP partition was /boot/EFI. The bootloader specification encourage to use /boot as ESP partition. So in this case, you can see bootloader entries. Boot is the ESP partition in this case. And you can see that every entry contains a particular name that makes it unique. We know also the architecture, x86-64. And we know a little bit of information that are just the information that are needed to be presented to the user when the boot manager shows up. So for example, we load our grab. These are all the information that grabs needs or systemd boot needs to shows this entry and correctly boot this entry. This is also important because with this we are able to boot the entry directly from the bootloader. We don't need to run grab make config. This is something that if everybody has installed Arch Linux, which I think many of us has done in the past, you needed to do grab make config. We don't need to do that anymore. This is actually a huge improvement. All distributions are able to provide their own menu entries, update them on their own, and the bootloader will grab them. Let's see what's written here. So we have the machine ID, which is actually the name, the first part of the name. Then we have the version of the kernel. We have the distribution title, which is Fedora in this case. We have the options for loading the kernel. So in this case, for example, we are passing which root file system we need to load. We pass in the unique identification. Then we also are passing where we can find the Linux kernel image and the initramfs kernel image. This path is relative to both to bootloader, and if you go inside the system, you can find that these actually exist, and they are the actual kernel images and initramfs. So instead of having /boot with the various kernel images installed there, we just know that they are here. So this also changes how we install a kernel. This is actually pretty pushed by systemd. So systemd is the one that provides a utility to install the kernel, which is called systemd kernel install, and it will install the kernel exactly where it needs to be. Second type of entries. So let's talk a little bit about FE unified kernel images. I know that somebody already did some presentation about that. I'm not going to talk in details about how they work. I'm just going to say that they are a standard, basically, that defines an image containing two important things and many other things if they are needed. The two important things are the EFI stub, which is basically the part required to be loaded by the firmware, by the bootloader. And the second part is the kernel image. So we have just this blob, basically containing the FEI stub and the kernel images. If we need anything else, options, other files, we can embed them as well. But the important part is that we can bring this, we can compile the kernel with this option, with the FEI stub option, and we can just bring it to the bootloader, and the bootloader will load this image. And directly load the kernel without passing through grab, systemd boot, wherever we want. We can just use that. How this format is created, how we compile Linux for that, is something that we are not going to see, but there are many resources online that are really, really helpful for that. Okay, we talk about bootloader support, but why are we not seeing it on our computers? Well, it's not really supported yet by Grab, because Grab2 has some patches that support for it, but the patches are not upstream yet. Basically, there is a fork there. It's working, but it's not upstream. So sometimes it's still needed before we are able to get it. But systemd boot supported since version 250, which is actually, I think, 1-2 years ago. It's actually a lot of time. And I'm testing a lot the microS images for SUSE, which we use systemd boot, and it works. We have the bootloader specification. You can download them and try. There's a couple of interesting pages that explain how it works, all the commands that are needed to actually replace grab make config and use systemd kernel install, sorry. Okay, let's add one little bit more step of complexity. So let's add the encryption. Right now, when you install a system, the installer usually asks you, do you want to encrypt the full system? And right now it's so cheap, the computer doesn't become slow. doesn't spend a lot of energy encrypting the system. So for us, it's just a check, and we need to remember the password. It's actually something that is pretty good. Okay, let's say that we are encrypting the entire system excluding /boot. What happens usually is that grub loads the kernel image, loads the initramfs, and by the time that the kernel is loaded, the initramfs starts, and that's the passphrase to unlock the system. So it asks you, please enter the password, otherwise you cannot enter, you cannot unlock the system, and you are locked out from it. This is actually not straightforward, but we have been using this for years in our Linux system, so it works. It's pretty well tested. But at the same time, there are a couple of cases where we might not want to add the passphrase. Let's say, for example, you have a workstation or you have a server installed somewhere. You know that if the system didn't get tampered on, nobody touched the system, you can say, I just want to unlock the system automatically. How are we going to do this? There has been a lot of work on this, but the key feature that we're able to allow this was the TPM 2.0. And I'm going to explain just a little bit of how it works and how we can use it to unlock the system. So first of all, one important part of TPM is that it's able to load to hold a key. We can just put any key inside there, and the key inside would be safe, at least for now. I know that a lot of people say that there is no such thing as safe, but let's assume that it's safe for now. And it's also able to compute PCR values, which we will be talking just a little bit later. And the important part is that all modern hardware is equipped with TPM2. Windows 11 doesn't boot if we don't have TPM2, so it's actually pretty well adopted right now. PCR, Platform Configuration Register. This is where the magic is. These are indexed registers that contain hashes, so think of an array, and every index contains a different hash, and every part of this, every index represents a different part of the boot process. So we have the FE firmware, we have the part where the kernel loads, we have the part with the secure boot, and so on. It's volatile, so basically every time we start it, we write some value, but by the time that the computer shut down, we don't have any value anymore. And it can be read, always, but it can only be set via an API, a secure API of the TPM, and we can pass a value. And by using that value, we will get the hash. So basically, we cannot tamper with the system. We cannot get the same hash by passing something else. If we change anything inside the boot process, if we change the firmware, then we will get a different hash. How are we going to use these PCRs? So let's see how we can use them. This is just a simple explanation. There are many things that I will not be talking about. I will try to simplify things as much as we can because we don't have a lot of time. So we have the key. We have the key of the encrypted disk, and we can put this key inside the TPM. So we have the key that unlocks the system. It may be a password or a random recovery key, whatever it is, we can just take this and ask systemd to put it inside TPM2. And while we put it there, for example, this case, the disk is dev SDA3, we also pass it this file called pcrlock.json, and this file contains the expected PCR values of the current boot. So we have this system boots. It gives us this pcrlock.json file, and we go to the TPM and say, look, this is the key. If the PCR values are the same, are the one that we are passing through this pcrlock file, then you can unseal this key. So this is a secure way to store the key and unlock the system automatically. This is not all there is to the command. There is actually another part. After we put the key there. We said what are the PCR values that we expect. Also, we need to create a policy. There are many arguments here that are passed to systemd PCR lock, but I just skip them. The important part is that we create this policy to the TPM and we say, look, we have put you the key, we have put you the PCR value. I'll use this key to unlock the system if the PCR lock are the same. We need to use both commands, unfortunately. As you can see, a lot of these commands are from systemd. Systemd right now supports a lot of things, and systemd boot, systemd PCR lock, systemd encrypted role are able to allow this this feature. We also need to make some changes to initramfs, because during the initramfs part, we usually we've been asked for the passphrase. Now we don't need to be asked for the passphrase anymore. We just need to check if the PCR lock are the same. We go to the systemd, and systemd goes to the TPM, and TPM unseal the key, and systemd unlocks the system. It's straightforward. If you see it like this, the implementation is not that straightforward, but let's keep it simple for now. There are actually quite some tools that are being used. These are the tools that are being used in MicroOS, and they will be used in Tumbleweed as well in a month or two. We can see systemd here is the main one. It allows for, it contains a bootloader. It allows for enrolling a key, creating policies inside the TPM, which is something not straightforward at all. You need to talk with the TPM. The code is, okay, it's actually pretty complex. Okay, let's skip to the last feature that we are going to see. Who knows kexec? Okay, quite some people. This is a feature that has been there for Linux for a long time. And basically we can say, we can go to the kernel and says, look, I want to boot a new kernel. Please freeze your entire memory, reset everything, and boot a new kernel without rebooting the system. This creates a couple of issues because, for example, the devices are already loaded inside memories. The kernel needs to pick up an uncertain state of the devices, of the firmware, and it gets quite messy. It has been there for 20 years, I think. I saw references of this in 2004, quite 20 years ago, quite a lot of time. So what did systemd do? Systemd added a new feature called software boot, and this is actually the command, systemd software boot. What happens is that instead of loading a new kernel, we can just ask systemd to shut down the entire user space, all the programs, and systemd itself will shut down. The kernel will stay the same, then systemd restart, and we have the system rebooted without passing through the hardware reboot, without loading a new kernel. So the kernel is still the same, the devices, the firmware, the kernel models will be the same. And it's been available since systemd 254, so 1 year. And another cool thing is that we can pin resources after reboot. So we can pass open file descriptors before and after the software reboot. So it allows for a lot of flexibility. This is it. Thank you for your attention.
Ci sono? Thank you, Danilo. Do we have any questions? There we go.
Hello, thanks for your presentation. Regarding the encryption of our system, how this way to encrypt, to full disk encrypt your laptop or your computer can protect us from a policy search?
Sorry, can you repeat please the last part?
A policy search, perquisition, or
okay. So, this is also a really interesting question. I think that in this case, especially for laptops, is not going to be useful. It's mostly made for workstations and servers, because one of the main use cases for this is, for example, when you have a server, you move the server somewhere else, and you want to be sure that nobody tamper with it, and you don't want to put the encryption key every time you boot the system. Actually, this is also something that needs to be regarded, because we don't want to have all our data read by someone else just because we didn't change anything in the system. This is something really important as well.
Any other questions?
I have a similar question, and I'm not from IT, so please be lenient when my lingo is not that specific or correct. So you asked about that it is possible with this new system that you can, like, you have a key, so when you reboot you don't need to type in your passphrase. Does this key stay the same, or does it will it be created every time a new key? So because I think that when you have the key stored and attacker can access just for a small time your system, the attacker could get the key, and when he has more time could start the system with this key if it's always the same key.
Thank you for the question. This is also something that is important as well. So what happens is that the assumption is that the key inside the TPM can never be read. So the TPM is developed in a way that the key stays there and no attacker could read it. If an attacker could read it, then it will be a problem. I know that maybe in a couple of years somebody will read it, but for now the assumption is that the TPM is safe. The key stays the same. And if we want to change the key, then we need to boot inside the system, enroll a new key, enroll a new TPM policy. So we need to do all the phases again from scratch.
Any other question? Thank you very much. Thank you, Danilo.
Thank you.
You lit up for us very obscure areas of the Linux system. Thank you, folks. Enjoy the rest of the day.